This is episode 2, A Nucleus in Making, and we are talking about atomic nucleus. Biology is governed by three general themes: genetic inheritance and mutation combine to dictate the concept of evolution through natural selection. This goes on to become the overarching theme in biological sciences. In this episode, we will introduce the first and most ancient theme, that is, the concept of emergent properties, that is, new properties emerge at successive level of organization. It should be kept very strongly in mind to better appreciate the design of our universe. You may go through the upcoming modern physics portion like a story if you like, and resume your studies when we reach an atom, which is officially claimed by chemistry. Modern physics is currently dabbling with a number of elementary particles divided into fundamental fermions and fundamental bosons. The scalar boson was observed with significant certainty at publicly famous CERN's Large Hadron Collider and was named Higgs boson. This particle gives rise to Higgs field permeating whole observable universe, and below a very high threshold value of temperature there is spontaneous symmetry breaking, affecting this field's interaction with other particles. Through such interactions only, other elementary particles, which are massless to begin with, gain their respective intrinsic mass, except photons, which continue to remain massless. Hypothetical gravitons are also predicted to be massless, while the result of Higgs interaction with neutrinos is still under speculation. Gluons are nearly massless after this interaction. The rest of the particles have substantial respective masses. The rest of the bosons, unlike Higgs boson, are directional, not scalar, and are called gauge bosons. These give rise to the four fundamental forces through their respective fields. Gluons gives rise to a 0.8 femtometer small range strong nuclear force field, which binds quarks carrying color charge to form a proton or a neutron. This is called color force. Two up and one down quark form a proton, while two down and one up quark form a neutron. Due to this, there is a very high positive potential energy in these nucleons, which translates into atomic mass as per m equals E by c square. This atomic mass is about 100 times more than the intrinsic mass of the constituent quarks. As you would recall, quarks gained this intrinsic mass due to the Higgs interaction in the first place. Gluons also bind protons and neutrons together to form atomic nucleus with the larger range strong interaction that operates at the distance of 1 to 3 femtometer. It is called nuclear force or residual strong force. This interaction adds a negative potential energy. Thus, all nuclei have a smaller mass than the sum total of its protons and neutrons. As a result, a fusion of small stable nuclei to form a larger stable nuclei will give off energy. For example, at the core of our Sun and other stars, nuclear fusion takes place. Alternatively, there are certain unstable nuclei which serves as nuclear fuel, giving off energy after nuclear fission reaction, giving rise to more stable, smaller nuclei. Photons give rise to electromagnetic force field and is responsible for interactions of particles that carry electrical charge like electron and proton. It thus forms atoms and then also molecules. Overall, it dictates the general form of all matter and enables us to see them as well. Particles like proton and neutron are called composite particles, as they are made up of two or more elementary particles. Similarly, atomic nucleus, atom, and molecules are all composite particles. There are two types of weak interaction. Charged current weak interaction is mediated by W bosons. It can change a lepton, like electron, into corresponding neutrino. It can also change the flavor of quarks. For example, a down quark becomes up quark by emitting a negative W boson, thus making a neutron into proton. This process is called beta decay, and the negative W boson quickly changes to electron and electron antineutrino. This beta decay is especially visible after nuclear fission reaction. The emitted radiation stabilizes the newly formed nucleus. Neutral current weak interactions is mediated by Z boson and are utilized by quarks and leptons to emit or absorb energy. Z bosons then decay into quark-antiquark pair 70%, neutrino-antineutrino pair 20% of the times, or lepton-antilepton pair 10% of the time. The gravitational force field is hypothesized to arise from gravitons and bind particles carrying mass together. Gravity is the weakest of the four fundamental forces. However, it is the dominant force at the macroscopic scale. For example, the orbital arrangement of our solar system is maintained through this interaction only. Graviton is considered a tensor quantity of rank 2, while other three gauge bosons are vectors, that is, rank 1 tensor. Just like biology begins with cells, chemistry begins with atoms. No chemical reaction can alter the nucleus of an atom. All the elements described in periodic table has its unique atom, or more specifically, the number of protons in its nucleus. Among all the subatomic particles we have studied, only the protons, neutrons, electrons, and electromagnetic field generating photons are required for the study of chemistry. An atom is originally neutral regarding its electrical charge. Thus, the number of protons and electrons are equal in an atom. Since chemistry is a play of electrons, the chemical properties of elements arise from the number of electrons intrinsically orbiting the nucleus of its atom. Thus, each chemical element has its unique number of electrons equaling the number of protons in its respective atom. This uniqueness is designated as atomic number. However, this atomic number is officially defined as the number of protons present in the nucleus. Because chemistry can alter the configuration of electrons arrangement but cannot alter the nucleus. Mass number is defined as the total number of protons and neutrons that makes up the atomic nucleus. Subtracting atomic number from mass number gives us the number of neutrons in that atom. Like here, this helium atom with atomic number of 2 and mass number of 4 has 2 protons, 2 neutrons, and in neutral atom 2 electrons as well. The mass of an atom is concentrated in its nucleus. The mass of electron is 2000 times smaller than that of proton or neutron, and hence we ignore it while calculating atomic mass. Neutron is slightly heavier than proton due to difference in quark structure. 1 by 12th mass of the readily available carbon-12 atom containing 6 protons and 6 neutrons was chosen as the atomic mass unit. The mass of a neutron and a proton is approximately equal to 1 atomic mass unit. However, in absolute terms, the mass of neutron is greater than mass of proton, which is greater than atomic mass unit, because the negative potential energy of large-scale strong interaction binding proton and neutron together in the carbon nucleus leads to slight reduction in the mass of carbon-12 atom and thus atomic mass unit. Remember that only small-scale strong interaction can impart positive potential energy, increasing the mass of bound system, because the magnitude of only this force increases with distance, like the stretching of a spring. It is also important to note that free state of two quarks is at near zero distance. This phenomena is different from other force fields like that of gravitation, electric, or large-scale strong interaction, which diminishes in magnitude with increasing distance. Thus, the free state for two particles with mass, electric charge, or residual color charge is at infinite light distance. Hence, they end up adding negative potential energy, making the system slightly less massive. Moving on, the accurate determination of Avogadro's number requires the measurement of a single quantity on both the atomic and macroscopic scales, using the same unit of measurement, like grams, as calculated here. Molar concept is built upon this. However, first experimental determination of this number was made by dividing charge carried by 1 mole of electron, that is 1 Faraday charge, which is equal to 96,485 coulombs, divided by the charge of 1 electron, that is 1.6 into 10 to the power 19 coulombs. Since each element is characterized by a unique number of protons in the nucleus of its atom, we can get isotopes of the same element by varying the number of neutrons present there. For example, carbon has 3 naturally occurring isotopes: carbon-12 (99%), carbon-13 (1%), and very rare carbon-14. They have 6, 7, and 8 neutrons respectively. Atomic mass ascribed to an element is weighted average of its natural isotopes. For example, carbon's atomic mass is 12.01 atomic mass units. Carbon-14 nucleus is unstable and undergoes beta decay, changing one of its neutron into proton by emitting an electron and an electron antineutrino to become a stable nitrogen atom with 7 protons and 7 neutrons. Statistics predicts the percentage of carbon-14 atoms that will undergo decay in a certain period of time. The time required for 50% of atoms to decay is called half-life. Half-life of carbon-14 is 5,730 years, while that of uranium-238 is 4.5 billion years. When an organism dies, it stops accumulating naturally occurring carbon isotopes, and by measuring the amount of carbon-14 atoms left, a fossil can be dated. Carbon dating can be done up to 75,000 years with the current measuring devices. Radioactive isotopes with higher half-life than carbon is used for dating older fossils. Sometimes indirect methods are employed where radioactive elements present in the sediments deposited in layers above and below the fossils are dated, and the fossil is assigned a date in between the two. It is used when the said element is not present in the body of organism, like uranium-238. Radioisotopes are also used in various medical diagnostic and imaging studies such as renal function test and PET scans. Now that we have studied the nucleus of an atom and the role of isotopes in biology, we will turn our attention towards the study of electrons and the emergent properties of atoms. In the previous episode, we have seen how a few elementary particles interacted with each other to give rise to emergent properties like mass, force field, and formed composite particles up to atoms. Here, we will look at behavior of electrons in an atom and build up the foundation of chemical bonds that give rise to molecules. When an electron comes in vicinity of a proton, they interact by the means of electromagnetic force field on account of the electric charge possessed by them. Photons thus becomes crucial in this interaction. A vital biological phenomena, photosynthesis, makes use of photons' interaction with the electron in chlorophyll molecule. Since the force is attractive in nature, with its magnitude decreasing with increasing distance, we ascribe a negative potential energy to this electron-proton system. The closer the electron is to proton, the more negative is the system's potential energy, which translates to more thermodynamic stability. However, the permissible energy states of the system, though infinite in number, is quantized, that is, only certain discrete values are allowed while others in between are forbidden. This happens because only certain paths fulfill the standing wave condition, where the wave-like arrangement of electron appear stationary with passing time from the proton's frame of reference. An analogy of a wave on a string with fixed end is helpful. However, the arrangement is more like a closed loop. De Broglie equation is used to link the wavelength of the wave nature with the momentum of particle nature. Now, this stationary condition is really necessary because any accelerated charged particle is bound to emit electromagnetic radiations in the form of photons as per Maxwell's equations. Thus, losing its energy, electron will keep moving closer to proton, making existence of atoms unstable. By solving the Schrödinger equation for an atom or a molecule, we can obtain the possible wave functions. Unlike molecules, angular momentum is quantized as well in atoms. As stated by the Heisenberg uncertainty principle, it is impossible to accurately measure both the position and momentum of a particle at any time. For very less massive particles like electrons, even 10% allowed error in velocity measurement throws the minimum error in position measurement to be greater than the supposed diameter of the atom as per Bohr's model. So, we cannot determine the trajectory of electron around an atom in the quantum mechanical model. We circumvent this problem by squaring the wave function of electron for a particular permissible energy and angular momentum obtained after solving the Schrödinger equation for, say, hydrogen atom. This squaring gives a position probability distribution, and its value at each point represents the probability of finding an electron at that point. The three-dimensional space enclosing the points, which collectively stands for 90% probability, is called an orbital. An electron in an orbital is characterized by four quantum numbers. The principal quantum number n denotes the average distance of orbital from the nucleus, and thus the energy of the electron as well. Its value can be any positive integer, with n equals 1 denoting the closest one, which is energy-wise the lowest, most negative, or most stable. One nodal plane is added in the orbital with each successive increase in principal quantum number. We can again invoke our string analogy to appreciate it intuitively. The second quantum number L is called azimuthal quantum number, and it denotes the angular momentum and shape of orbital. Its value ranges from 0 to n minus 1. For example, for n equals 3, L equals 0, 1 and 2. Shape is spherical for s orbital with L equals 0, dumbbell-like for p orbital with L equals 1, and core-lobe for d orbital with L equals 2. Any non-zero value of L must have an angular dependence, and thus such orbital cannot be spherical. This keeps the electron a little farther from nucleus as compared to orbital with lower L values. In multi-electronic system, within a set of orbitals with a particular value of n, the energy increases as L increases, because with increasing L value, the orbital shape allows lesser penetration near nucleus. This leads to better shielding of nuclear charge by electrons of preceding orbitals, causing less negative binding energy for that electron. As a useful rule of thumb, the sum of n and L is used to arrange orbitals in increasing order of binding energy, that is, from the most negative to least negative. Thus, the Aufbau principle to build up an atom follows the diagonal rule. The third quantum number m is magnetic quantum number. It describes the orientation of orbital in a particular direction. For every value of L, m can take integer values from minus L to plus L. For example, for dumbbell-shaped p orbital with L equals 1, m can be negative 1, 0 and positive 1, representing the three possible orientation towards x-axis, y-axis and z-axis. Similarly, for d orbital there are 5 possible orientations and f orbital has 7 possible orientation. A spherical s orbital can only have one orientation, hence for L equals 0, M equals 0. Lastly, there is a spin quantum number, S, which can either have a value of plus half or minus half, and denoted by up arrow and down arrow respectively. It points towards the fact that for any given standing wave, there can be another wave with coinciding nodes and a phase separation of 180 degrees at all times. Thus, there is a specific position probability distribution for any given value of n, L, and M, which is called an orbital, and each of these orbitals can have up to 2 electrons, each having a specific value of S, as stated formally by Pauli principle. In filling up of electrons in a neutral atom in ground state, Aufbau principle applies, where electrons fill up available orbital with lowest energy first. In addition to this, Hund's rule states that if multiple orbitals with equal energy is available, electrons would fill unoccupied orbital first before pairing up with other electron in half-filled orbital. For example, carbon's configuration is 1s2, 2s2, 2p2, while silicon's configuration is 1s2, 2s2, 2p6, 3s2, 3p2. The configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. However, copper's configuration is 1s2, 2s2, 2p6, 3s2, 3p6, then 4s1 and 3d10. Here, one electron from 4s level occupies 3d orbital because the extra stability gained by the symmetry of d orbital outweigh the slight difference in energy level of 4s and 3d level. So, some finer points regarding energy level help explain the exceptions. Number 1. The energy of nth p orbital is moderately higher than that of nth s orbital, but it is considerably lower than that of n plus 1th s orbital. Thus, ns2 np6 is called closed shell configuration. Hence, the elements are considered non-reactive if they attain this configuration, with all inner shells occupied. Helium and nearby elements are exceptions, as they are only required to attain 1s2 condition. Number 2. The energy of nth d orbital is comparable with energy of n plus 1th s orbital, but lower than the energy of n plus 1th p orbitals. Hence, the symmetry-driven exceptions like copper and chromium. Number 3. The nth f orbital is comparable in energy to n plus 1 d orbital. Hence, the unique lanthanides and actinides configurations. One of the great merits of modern atomic theory lies in its ability to interpret elemental behavior in terms of the electronic structure of atoms. The periodic table separates out into 4 blocks of elements, in which the s, p, d, and f orbitals respectively are last to fill up. The elements of group 18 with completely filled outermost shell, that is ns2 np6 configuration, also called closed shell configuration, are designated inert or noble elements. The rest of the elements of S and P block have one incomplete outermost shell, that is nth shell, and are called representative elements. The D block elements have two unfulfilled outermost shells, with nth shell only having s orbital electrons and n-1th shell having unfulfilled d orbital. These are called transition elements. These elements show properties like colored ion, multiple valence shells, and coordination compound formation. Similarly, the F block elements have three incomplete outer shells and are called inner transition elements. Now, most elements have 1, 2, or 3 extra electrons, while most non-metals have 1, 2, or 3 less electrons as compared to the closest closed shell configuration. Moreover, alkali are those metals that need to give up only a single electron, and halogens are those nonmetals that need to take up a single electron. The closed shell configuration of Ns2Np6 is achieved by losing, gaining, and sharing electrons by other elements. In the next lesson, we will learn about bond formation and molecular structures. We have seen how a closed shell configuration is energy-wise very favorable, and after attaining such a state, a chemical species becomes inert regarding its chemical behavior. There are numerous ways of achieving this. We will begin our discussion with the strategy of sharing electrons, which leads to formation of covalent bonds. These bonds are most prevalent in nature, and they also provide us with the necessary background to understand other kinds of chemical bonds. While building up electronic structure, we followed the principle of minimum energy. That same thermodynamic principle fixes the number of atoms in a molecule, their ordering, their relative spacing, and the overall molecular shape. Hydrogen molecule ion or dihydrogen cation is the simplest molecule comprising of two protons sharing one electron. Its exact quantum description has been worked out. Infinite number of discontinuous quantized energy states are available. The wave function describing each energy state, when squared, gives the position probability distribution for electron in such state. For mapping such molecular orbital, the internuclear distance is determined to be that for which the electrostatic potential energy of the system is lowest. When occupying the ground state molecular orbital, it is interesting to note that electron is more likely to be found in the region between the two nuclei. This cement of electronic cloud accounts for the increased stability of molecule compared to free atoms. Hence, we conclude that the energy of electrons is quantized in molecular orbitals, and molecules form because electrons are able to experience attractive electrostatic force simultaneously from both nuclei. To ease up calculations, we tend to use approximate methods to determine molecular orbitals in multi-electronic system. Molecular orbital theory suggests that approximate molecular orbital wave function can be constructed by linear combinations, meaning addition or subtraction, of corresponding atomic orbitals of constituting atoms. This method was tested against exact solutions of hydrogen molecule ion and then extrapolated to other systems. However, after squaring the resulting wave function, there is a slight underestimation of the electron density in the internuclear region. Hence, it is aptly called an approximate approach. Adding the atomic wave functions forms constructive interference orbitals localized largely in the internuclear region, while subtracting them forms destructive interference orbitals located away from internuclear region. The former, having lower energy, is called bonding molecular orbital, while the latter, having higher energy, is called antibonding molecular orbital. Algebraically, it can be represented as shown, with the final term contributing to the change in probability distribution. So, we construct approximate molecular orbitals, arrange them in sequence of increasing energy, and then place electrons in the orbitals following analogies of Aufbau's principle, Hund's rule, and Pauli principle. Also, analogous to s, p, d, etc. atomic orbitals, we have sigma, pi, delta, etc. molecular orbitals. Whenever two atomic orbitals combine along the internuclear axis, a bonding and an antibonding sigma orbital is formed. And when two atomic orbitals perpendicular to internuclear axis combine, a bonding and an antibonding pi orbital is formed. For example, s orbitals can only form sigma bonds, while p orbitals form one sigma bond and two pi bonds. Sigma, pi, and delta orbitals have 0, 1, and 2 nodal planes respectively. A general energy-wise schema for molecular orbitals is shown here. Note that the sigma and pi bonding orbitals at p level is comparable in energy, and their exact sequence is sensitive to the number of electrons present there. For example, in nitrogen, oxygen, and fluorine diatomic molecules, sigma bonding orbital has lower energy and fills earlier than corresponding pi orbital. For example, the electronic configuration of homonuclear diatomic nitrogen molecule is sigma bonding 1s2, sigma antibonding 1s2, sigma bonding 2s2, sigma antibonding 2s2, sigma bonding 2pz2, pi bonding 2px2, pi bonding 2py2. Here, the total number of electrons in bonding orbitals is 10, and that in antibonding orbitals is 4. Bond order is defined as half of the difference between the number of bonding and antibonding electrons. So, it is 3 for this nitrogen molecule. The positive bond order implies a stable molecule, a bond order of 1, 2, and 3 corresponding to the classical single, double, or triple bond, respectively. Hence, bond order is inversely proportional to bond length as well. Bond order of diatomic oxygen molecule is 2 and diatomic fluorine molecule is 1. A zero or negative bond order implies unstable molecule. There is no classical analog of fractional bond order. For example, NO has a bond order of 2.5. Molecular orbital theory can be further extended to explain polyatomic heteronuclear molecules as well, and it is more appropriate for predicting ionization energies and the positions of spectral absorption bands. However, we can skip this tedious approach in favor of hybridization when it comes to determining the shape of molecules. Instead of combining the corresponding orbitals of the combining atoms as in molecular orbital approach, in hybridization we combine all the electron containing orbitals of valence shell of the central atom. In the previous episode, we discussed the finer points of energy level of atomic orbitals. Using them, we can state that nth s orbital is energy-wise comparable to n-2th f orbital, n-1th d orbital, and nth p orbital. Hence, we promote one of the electron from s to a slightly higher energy orbital to increase the number of electron containing valence shell orbitals by 1. This one extra bond more than compensates for the energy required for electron promotion. Let us apply this promotion cum hybridization principle for carbon and oxygen atom to form methane and water molecule. Both undergo sp3 hybridization, meaning 4 equivalent theoretical atomic orbitals are proposed, each having 1/4 s orbital character and 3/4 p orbital character. To maximize mutual spatial separation, each orbital arrange themselves towards the vertices of tetrahedron with nucleus at the center. Next, we overlap these hybrid orbital with the s orbital electron of hydrogen as per valence bond method, taking care of opposite sign of overlapping orbitals. It forms tetrahedral methane with bond angle of 109.5 degrees each, and bent water molecule with bond angle of 104.5. The reduced bond angle of water is explained by extra electronic repulsions from the two lone pairs. Similarly, depending on type of hybridization and electron pair repulsion, different molecular shapes are explained. Carbon compounds and water are very crucial for biology. Carbon atoms can form double bond as in ethene or ethylene by undergoing sp2 hybridization after electron promotion. The left out p orbital forms a pi bond perpendicular to the planar structure. Similarly, in ethine or acetylene, Carbon undergoes sp hybridization, forming a triple bonded linear structure with two mutually perpendicular pi bonds. In a benzene molecule, each carbon is sp2 hybridized, making two carbon-carbon sigma bond and one carbon-hydrogen sigma bond each. There is two equally valid way of arranging the remaining p orbitals to form pi bond as per valence bond approach of orbital overlap. Since there can be only one arrangement, we apply the concept of resonance in all cases of more than one equally valid electronic arrangement, which adds to the molecular stability. Intuitively, we can also invoke the molecular orbital approach for this last part. We can combine these 6 p orbitals, each from different carbon atom, to form 6 molecular orbitals. The lower 3 orbitals are bonding type pi orbitals and accommodates the 6 electrons. It forms a cloud of electron above and below the planar ring. This approach is more valid as it explains the presence of closely spaced quantized energy orbitals in carbon ring structures, enabling them to absorb low energy radiations of visible spectrum, for example, chlorophyll, heme, etc. The bonded electrons are often shared unequally between non-identical chemical species. For example, electron pair of the OH bond in water molecule is shifted towards more electronegative oxygen, making them polar covalent bonds. Hence, water molecule gains a dipole moment. Elements that require high input of energy to break one of its valence electron away and releases high amount of energy after gaining one electron in its valence shell is more electronegative. Similarly, elements with low ionization energy and low electron affinity is relatively electropositive. When the low ionization energy of an electropositive atom is more than compensated by the high electron affinity of the electronegative atom and the Coulomb force operational between the two would-be ions, then electron transfer occurs. This arrangement is called ionic bond, and it is particularly strong between highly electronegative halogens and highly electropositive alkali. We can place non-polar covalent bond, polar covalent bond, and ionic bonds on one spectrum of increasing electronegative difference. There are certain weak chemical bonds which are equally important in biological sphere. Any polar covalent bond gives partial charge. For example, oxygen carries partial negative charge and hydrogen carries partial positive charge in a water molecule. This hydrogen can interact with adjoining chemical species carrying partial or complete negative charge, be it oxygen from another water molecule, nitrogen from dissolved ammonia, or chloride ion from dissolved salt. These interactions are called hydrogen bonds, and it makes water very special. Another weak bond is van der Waals interactions. It operates when two chemical species, even non-polar ones, come close enough for opposite ends of instantaneously generated dipole moment to interact. It is important to note that electrons are not always symmetrically distributed, and this momentary asymmetry can induce an opposite dipole in a nearby chemical species. Both Spider-Man and lizards have thousands of tiny hairs with numerous secondary projections at the tip of their limbs. This vastly increased surface area makes individually weak van der Waals interactions strong enough to support the creature against the gravity. Biological macromolecules maintains their specific three-dimensional shape with the help of hydrogen bonds and van der Waals interactions. Now, with this background, we are ready to take a tour of primitive Earth to probe into the origin of life on Earth. As we have learned in the previous episodes, how basic science is slowly structuring our universe. In this lecture, we will begin gaining an aerial view over the major events of 4.6 billion years of Earth concerning life. A long time ago, somewhere in the womb of our galaxy Milky Way, a star exploded. The debris from this supernova rattled through space, forming shock waves of materials. At one locus of this compressed dust, a spark of nuclear fusion was given off, and our Sun was born. Some smaller condensations in the surroundings gave rise to planets, while the rest floated as asteroids, completing our solar system around 4.6 billion years ago. The journey of Earth has been divided into four eons. The first one is Hadean, spanning from 4.6 to 4 billion years ago. It was an astronomically violent period for Earth, being constantly bombarded with huge chunks of rocks and ice. One particularly heavy collision, with the line of impact fortunately deviating from the center of Earth, threw some part of Earth tangentially, giving rise to the Moon 4.5 billion years ago. The constant collisions caused all water to remain in vaporized form due to excessive heat generation. The atmosphere was thick with water vapor, and volcanic gases like nitrogen oxides, carbon dioxide, methane, ammonia, hydrogen, and hydrogen sulfide. After the end of the late heavy bombardment period, around 3.9 billion years ago, the Earth began to cool down, and water condensed to form oceans, and much of hydrogen escaped into space from the atmosphere. A crust of solid rocks was thus formed over the molten Earth, with oceanic water occupying depressions of this rocky surface. Oldest fossil of cellular life are dated to 3.5 billion years ago in the form of stromatolites. These are formed when certain prokaryotic cells gain ability to bind thin films of sediments together. Thus, the first cell must have been formed much earlier, say around 3.8 billion years ago. The appearance of solid rocks and oceans accompanied by first cellular life forms on Earth marks the early events of the second eon, Archean. Now, let's look at the formation of first living cell in detail. Logically, four steps must be fulfilled to manufacture a cell. First, the abiotic, that is, without any help of living organism. The abiotic synthesis of small organic molecules, such as amino acids and nitrogenous bases. Second, the joining of these small molecules into macromolecules, such as proteins and nucleic acids. Third, the packaging of these molecules into protocells, that is, droplets with membranes that maintain an internal chemistry different from that of their surroundings. And fourth, the origin of self-replicating molecules that eventually make inheritance possible. In 1920s, A.I. Operin and J.B.S. Haldane independently hypothesized that primitive Earth's environment was reducing in nature, as assessed by the presence of electron donor species, such as methane and ammonia. This could facilitate formation of organic compounds with an input of extraneous energy, for example, from lightning or UV radiation. Thus, oceans mixed with organic molecules can be seen as a primitive soup from which life arose. In 1953, Stanley Miller, working under Harold Urey, tested this Haldane-Operin hypothesis in his famous Miller-Urey experiment. In this setup, water from ocean flask was heated to reach atmosphere flask which contained methane, ammonia, and hydrogen. Such was the proposed atmospheric constituents back in 1950s. Sparks were discharged into this atmosphere flask to give the lightning effect. Atmosphere flask was then condensed to mimic rain and drained back into the ocean flask. This cycle was repeated several times and a sample was taken for analysis. The sample contained amino acids, hydrocarbons, and simple compounds like formaldehyde and hydrogen cyanide. Miller also conducted experiments mimicking volcanic conditions of the primitive Earth. Later, some challenged the amount of methane and ammonia present in primitive Earth's atmosphere to make it reducing enough, and in this revised model, a nitrogen and carbon dioxide based atmosphere is neither reducing nor oxidizing. Recent Miller-Urey type experiments with neutral atmosphere flask has also yielded organic molecules. Again, even with such neutral atmospheric assumptions about primitive Earth, packets of reducing environment was proposed to be available near openings of volcanoes and deep sea vents. So, in 2008, the sample saved by Miller from volcanic conditioned experiment was reanalyzed using modern methods. It revealed mass of amino acid to be double than that of his classical experiment. Thus, Miller-Urey type experiments demonstrate that the abiotic synthesis of organic molecules is possible under various assumptions about the conditions of primitive Earth. Thus, the prospect of abiotic synthesis has been proved beyond significant doubt. Additionally, another source of organic molecule could have been the meteorites of the carbonaceous chondrites type, which contain 1 to 2% carbon compounds by mass. In 1969, one such chondrite fell in Australia, dated to be 4.5 billion years old, and contained more than 80 amino acids along with lipids, simple sugars, and nitrogenous bases, including uracil. Moving on to the second condition of forming large polymerized organic molecules, a 2009 study showed a spontaneous polymerization of RNA molecules from precursor monomers. Additionally, by dripping amino acid or nucleotide solution over hot sand, clay, or rock, researchers have procured polymers without the help of any enzyme or ribosome. Polypeptide chains were however not a linear one as found in proteins, yet these polymers could have acted as weak catalysts for further more diverse polymerization reactions on primitive Earth. The third condition of protocells can be assessed in vesicles that form spontaneously when lipids are added to water. They arrange themselves in bilayer similar to plasma membrane. The fluid compartment enclosed by the vesicle is separated from the rest. The vesicles can grow in size without breaking membrane continuity, and they can also divide into two. Mont Morillonite is a soft mineral clay formed by weathering of volcanic ash and must have been abundant on early Earth. When it is added to the solution, the organic molecules, including lipids, get concentrated on its surface, and the rate of vesicle formation is enhanced. These vesicles can also absorb Mont-Morillonite particles with other organic molecules attached to them, such as RNA. Also, the lipid bilayer shows selective permeability, facilitating metabolic maintenance of inner compartment constituents using outside source of reagents and reactions. Now, coming to the step 4. According to widely accepted RNA world hypothesis, the first self-replicating organic molecule was RNA. Thomas Sheck and Sidney Altman found that RNA performs various catalytic functions in the cell similar to protein-based enzyme and named them ribosomes. RNA, being single-stranded, can assume a variety of specific three-dimensional structures as mandated by its nucleotide sequence. Certain ribosomes catalyzed the process of making complementary copies of short pieces of RNA if nucleotide monomers are available. Some of these sequences could multiply faster and with lesser errors in certain environmental conditions, resulting in more copies of that sequence. Occasionally, a copying error could produce a sequence which is structurally more stable, copies more quickly, and is more adept in maintaining favorable environment within the vesicle. Vesicles containing such RNA had more self-replicating metabolic machinery than others. Some of these vesicles could grow and divide, distributing copied RNA materials to daughter vesicles. RNA performed the function of present-day DNA and protein in this precursor RNA world. Natural selection was operational at molecular level to give rise to more efficient and in the process more sophisticated protocells. Later, Less reactive deoxynucleotides could have been employed in RNA replication, giving rise to DNA molecule which was chemically very stable in its double helix form. Thus, natural selection favored protocells having DNA for storing information of effective nucleotide sequence as it was less likely to mutate. Also, some ribosomal RNA could catalyze polymerization of amino acids into polypeptides. These polypeptides, like RNA and unlike double helix DNA, could assume diverse three-dimensional structures. Hence, they were able to catalyze various novel reactions. This gain in new functions led to increased probability of survival and multiplication for such cells. Hence, clans of cells developed, with information stored securely within DNA, with effective execution of various functions by proteins, and RNA serving as intermediary between the two, in an environment segregated by lipid bilayer, and life blossomed.